Hey everybody, this is Professor Ross. This video is about sampling from a finite population. So we're going to be talking about what are the best ways to get a sample to make sure we avoid some problems um, that we can see in samples, and talk about a good ways to get a good sample from a population. So let's take a look at some notes here. And oops, didn't mean to do that. We're talking about sampling from a finite population. One of our key learning objectives for this whole unit is to be looking for ways to recognize potential biases in sampling, including in surveys. So, going to contrast infinite process versus a finite population for a few minutes. We have talked about infinite processes a little bit, or what we could consider to be an infinite process. For example, we talked about teaching someone to play rock, paper, scissors, and then giving them 12 trials and seeing how they do. We call that an infinite process because we could theoretically at least keep playing rock, paper, and scissors forever. And those 12 trials are a sample of that long process. The parameter in that situation is a number about that long run process. For example, we looked at what proportion of the time would someone throw scissors. The statistic is the number about that sample, just those 12 trials. So statistic about the sample, parameter about the whole thing. We have a parallel kind of scenario, and even when we don't have an infinite setting, when we're talking about a finite population. So we use the word population in statistics to mean all individuals of interest. So for example, you might be interested in all the students at our college, or all the people in our country, or all the people in your hometown, um, or all the squirrels in East Tennessee, something like that. That's the population. Once again, we have a parameter that's a number about the entire population. A census lets us know what the parameter is, because in a census, we get data from the entire population. So that's really great when we can manage a census. The thing is, censuses are actually pretty hard to accomplish. They take a lot of time and resources, and sometimes it's not even really feasible to do a census. For example, let's say you wanted to do a census of all squirrels in East Tennessee. Well, actually tracking down every single squirrel and gathering whatever data you needed about the squirrels is going to be next to impossible, right? So, because censuses are generally not feasible, uh, instead we do a sample. And instead of looking at all the individuals, we look at a subset of individuals, and we calculate a statistic, which is a number about our sample. So we take the data from our sample and calculate a statistic from that. We hope the statistic gives us some insight into the parameter, because we're not actually going to find out what the parameter is, but we'd like to know something about it, and that's what the statistic can do for us. So a key question then becomes, how do we choose a sample so that we can feel good about this statistic actually representing the parameter in a fair way? How do we choose a sample? Let's take a look at an example. Let's say we wanted to choose a sample of Maryville College students, and we wanted to ask them some things, maybe ask them about what their GPA is, maybe ask them whether they're a commuter or resident. Why not do a census of all Maryville College students? It might not be too bad to do a census, especially if you're, say, the registrar and you have access to all students' academic records and you can get their GPAs. Um, on the other hand, just for a plain old student to do a census, now you've got to track down every single Maryville College student, and that takes a lot of time and effort. So instead, we might try a sample. What if we asked the first 30 students that we saw early in the morning on campus? Let's say we get out to campus early, and we just find the first 30 students we see walking around. Would that be a good way to get a sample of Maryville College students? I encourage you to pause the video and think about whether that would work well or if there'd be any issues. So if we're asking them about their GPA, and we're only talking to students who are up early in the morning, maybe students who tend to stay up too late at night doing other kinds of stuff and not working on their schoolwork are not up early in the morning. They're sleeping in and skipping classes, and maybe we'd miss out on students who have lower GPAs because of that. A potential problem like that we term as bias. Let's think about commuter or resident. Maybe on campus early in the morning, it might be more likely that you'd see residents around because commuters haven't arrived to campus yet. So that could also be biased. What does bias mean? Bias means, and bias is one of those words that kind of has a day-to-day meaning. We talk about something being biased day to day, but in statistics, it means something very specific. It means when our statistic from a sampling procedure is consistently different from what the parameter would be. So in our case, the parameter for GPA, what the real average GPA is for all of campus might be 3.0, but our early morning procedure would tend to give us statistics that are more like 3.3. Now they wouldn't give us that every time. A sample might vary, but if over and over again we did this process and they tended to be a little bit higher than the real average GPA, that would be called bias. Or in the case of commuter or resident on campus, we might have a proportion of commuters like 0.7, but early in the morning, over and over again, we did samples, we might find, 0.85 or zero 0.9 or something like that. So it might be biased because that statistic from the sampling, if we tried that sample over and over again, we'd see it would actually be different from the true parameter. So that's what bias means. We don't want bias. We want to avoid it because we want our statistic from a sample to give us a good picture of the parameter, not to be off from what the parameter is. Now you'll notice that we might have suspicion of bias here, but something like hair color, we might feel less suspicion of bias in the same sample. Early in the morning, is it more likely we're going to see people with brown hair? Doesn't seem very logical. So we might feel okay about this kind of sampling if we're trying to find out hair color, whereas we might not feel okay about this kind of sampling if we're trying to find out GPA or commuter resident. So we got to think about how we get a sample, and we always want to ask ourselves, is there something about the way I'm getting the sample that may cause bias? Unfortunately, sometimes we're not aware of the kinds of things that would cause bias, and so statisticians have kind of a gold standard for a way that they believe will do a good job of eliminating bias. Our goal is to eliminate bias and to get what we call a representative sample, that is a sample that represents the population really well. How can we get a representative sample? The key is to use a random procedure to get our sample. So something that's truly random in the process. Why do we feel like that? Well, if our process is random, then it should take everybody from the population and give them some kind of chance to get into our sample. And so the most common and simplest approach to this is called a simple random sample. And a simple random sample just means that every observational unit, every individual, has equally likely chance of being in your sample. So if we're talking about Maryville College students, then we would want every student at Maryville College to be equally likely to end up in our sample, and that would be a simple random sample. How could we do that? How could we make sure everyone has an equally likely chance of getting in? Well, we've already seen a problem with maybe just showing up to campus and walking around and looking for students. We might be biased against commuters or something like that. So a better way would be to take, and this is kind of the common procedure for a simple random sample, take a list of all of your observational units, here all Maryville College students, and use some kind of random process to choose students off that list. So we could use a random number generator and just have our list numbered and randomly pick students off of that list. Or we could take all those students' name, write them on same size pieces of paper, cut them up, put them in a hat, shuffle them all around, draw students' names out of the hat. So we can do physical things that give us random samples. We can also, most of the time, we're doing some kind of technology that's using a random generation to choose um, individuals from our population. You'll notice that this can work really well when you have a list of the whole population. Like Maryville College, we have a list of all the students. That can work really well. It's a lot harder to do a true simple random sample when we don't have a list of the whole population. Once again, let's talk about East Tennessee squirrels. Nobody has a list of all the squirrels in East Tennessee. We can't put them on a list and randomly pick them and then go find them. Um, but we still can use some random procedures to get a sample in a case like that. Like we might divide up East Tennessee into regions and then randomly pick some regions and then divide up those regions into quarters and randomly pick some quarters. And then we might go and try to get a couple of squirrels from each randomly selected region. So we can do things like that that will help eliminate bias and give us a good representative sample. Right? We say random samples result in unbiased estimators for the parameter, both proportions and means. So if we do a good job getting a random sample, then the statistic from our sample should give us a good estimation of the parameter, which is exactly what we want. Take note that sample size does not impact bias. And this is a real important thing to keep in mind. Bigger samples from a biased procedure are not any better. If you've got a process that introduces bias into your sampling procedure, you can't fix it by taking a bigger sample. If you get to the point where you've done a census and you've talked with or gotten data from every single individual, then that's big enough to reduce bias. But otherwise, the size of the sample does not impact bias. It's all about the technique used to choose that sample, and we always want something random involved in that technique. Couple of symbols for you to be aware of and take note of. We have different symbols for the statistics that we talk about from our samples versus the parameters that we talk about from our population. You'll note that the symbols for statistics are all letters from our alphabet, P, X, and S. The letters for the parameters are all letters from the Greek alphabet, pi, mu, and sigma. So that's one thing that's kind of nice to note. Whenever you're looking at a symbol and it's a letter from the English alphabet, you know that that's something related to the sample. Whenever it's a letter that's from the Greek alphabet, that's something related to the population. We've seen these categorical ones before. P hat, that's the proportion of successes in our sample, versus for the parameter, pi is the proportion of successes for the whole population. Similarly, we have parallel kinds of ideas for when we're talking about quantitative variables. X bar is the mean for a sample. Mu is the mean for the entire population. And so this letter here is the Greek letter mu. And it kind of looks like a U with a little tail on the front of it, or maybe a pointy M. And that's the Greek letter M for mean. Similarly, we use a S for standard deviation from a sample, and we use the Greek letter S for standard deviation in the population. The Greek letter S we call sigma. It's going to be really valuable for you to get comfortable with those symbols and real familiar with them. So I encourage you to take some time, maybe even make yourself some flashcards just to get used to all those different symbols, because we'll be using them plenty throughout the course. All right, so we want to draw a random sample. How do we use it? When we use a simple random sample, we eliminate bias from the sampling procedure, which means that our statistic from our sample should do a good job helping us estimate the parameter. The result is a representative sample. The statistic from the sample, either our p hat for a proportion or x bar for a mean, we feel is going to be in the ballpark of the parameter. We know it's somewhere in the neighborhood of the parameter. Now, it may not be exactly the same as the parameter, but we feel like it's somewhere close. And that's where our inferential procedures can help us decide how close we are and what the parameter might be like. So results from a random sample from a finite population have variability. For example, if I took a sample of Maryville College students and looked at the proportion of commuters, and you took a random sample of Maryville College students and looked at the proportion of commuters, we wouldn't have the same proportion, but they should both be in the same neighborhood, right? So that's something that's worth noting. There is variability. When the population is at least 20 times larger than the sample, random sampling from a finite process acts the same as from an infinite process. So we talked about how there's some differences between a finite population versus an infinite process. But the nice thing is that when the population is big, they both act the same, and thus we can use the same simulation or theory-based approaches. We don't have to take a whole different a whole different approach when we're using a finite population, as long as our population is big. And for the most part, that's always going to happen. We don't really have to worry about that. So this is really good news. Put a smiley face on this. This means we don't have to learn whole different techniques. We can use the same ones we've been learning all along. Summing up, sampling from an infinite process or a large finite population act the same. We want a representative, unbiased sample so we can generalize to the population, and we must use a random sampling procedure to get that.